All right, my friends, welcome back. Some questions some of you have asked that I think are relevant to everybody. Some of you want to know, will you have the sheet that shows the structures of the functional groups, their prefixes and suffixes, and relative priorities on the exam? And the answer is no, I do not intend to put that on the exam. However, no, I mean, you're not going to have a sheet on the exam. There's going to be a handful of nomenclature questions on the exam. They're all going to be multiple choice. There will be some E and Z stuff. Now, nothing's going to save you from not recognizing a functional group. Nothing's going to save you from forgetting the suffix or a prefix. However, memorizing the relative priority is not as hard as you think. And the reason for that is that the priority list shown in the study guide divides everything up into basically three groups. There are dotted lines, and they are there for a reason. You will see that there are groups above the first dotted line that all have, and I'm not even drawing them in relative priority, I'm just drawing them all as part of the same overall group. But if you look at what all of these functional groups have in common, their functional group has 3 bonds between carbon and some electronegative heteroatom, where Z equals something more electronegative than carbon, like nitrogen, oxygen, halide, and so on. All of these functional groups have 3 bonds between carbon and some electronegative heteroatom. And you'll notice that in all the examples in the study guide, there were none of them that had, say, an acid and an ester, and you had to try to decide whether the acid or the ester was higher priority. That's intentional. I don't intend for you to know or care whether the acid is higher in priority than the ester. It is, but I don't care, and I just forgot it, right? It's already gone. So don't worry about relative priorities among this group of molecules. There was a dotted line, and then you have the ketone and the aldehyde. There is a rule for whether the ketone is higher in priority than the aldehyde. I don't care what it is. Both of them have 2 bonds between carbon and an electronegative heteroatom. What you do need to realize, and you can do this without memorizing insofar as you can count, that the aldehyde or the ketone is lower in priority than the carboxylic acid or the ester. Do you see how you do that? Some of you are doubting your ability to do that without having memorized a list. Again, focus on the carbon in the functional group. How many bonds does it have to an electronegative heteroatom? That helps you decide without a lot of trouble that the amide is higher in priority than the aldehyde. Okay? Similarly, there's another sort of dotted line, and you have here things like alcohols and amines, thiols. I do not care whether the alcohol is higher in priority than the thiol or the amine, but what's important is that all of these have 1 bond between carbon. The functional group itself has 1 bond between carbon and an electronegative heteroatom. If you can group those in those 3 groups, that's going to help you decide who the highest priority functional group is. You are going to have to memorize that this is a ketone. Can't help you there. Sorry. You are going to have to memorize that the appropriate suffix for a ketone is -one. Can't help you there. You got to do that. Okay? Yes?
Just out of curiosity, is the relative priority similar to the pKa?
Does relative priority follow pKa? No. As far as I can tell, it's arbitrary. Somebody just decided. Yeah. Okay. So I want to spend a minute or two, a few minutes going through one more example of sort of nomenclature in E versus Z. What's the highest priority functional group in this molecule? Comes straight out of your study guide too. So some of you may have done this already. If you haven't, well, we'll do it now. But you ought to be able to do it on your own. Yes?
I was just wondering, what is the 3 bonds, 2 bonds? Because they both have 3 bonds. I'm just confused on that.
Right. 3 bonds to what? 3 bonds to something that's more electronegative than carbon. 1, 2, 3. See it? 1, 2. Sorry, wrong. I meant to do that on the ketone or the aldehyde. And then 1. That's the difference, yep. Okay. Right, so highest priority functional group here. I can see it. Can you see it? That's not sufficient. Tell me what it is. Somebody say an acid chloride. Okay, good. All right, there it is. The suffix, the appropriate suffix for that is oil chloride. It's supposed to be unpronounceable. That's all right. Let's see. Now we need the root. The root, we got to decide the longest chain of carbons it contains, the highest priority functional group. I mentioned this a couple of times in office hours. I know that you stay up late at night worrying about these things. We're going to talk about how to number the chain. And for the groups like, say, these highest priority ones, where because they have 3 bonds to something that's not carbon, they are necessarily at the end of the chain. Then it's easy. You just start at carbon 1 and start numbering from the highest priority functional group. But I know you wish to anticipate lots of different possibilities. So some of you are worried about this situation where you have a ketone and it's in the middle of a chain, and you're wondering, do I number 1, 2, 3, 4, 5, 6? Or do I number 1, 2, 3, 4, 5, 6, right? And many of you were awake at some point in the night. Never mind, you don't have to tell me, worrying about that. There is a right way to number it. The right way is in blue. You number it so that the highest priority functional group has the lowest possible number. However, my standard for answering nomenclature questions is, does your answer unambiguously describe the structure of this molecule? With 6 carbons, the correct name would be 2-hexanone, but I'm going to tell you that even if you wrote 5-hexanone, I would give you credit for that because that unambiguously describes the structure of the molecule. It's not technically right, but we prefer meaning over arbitrary syntax rules. Now, I'll just tell you, you're going to be writing anything, or you don't have to write anything on a multiple choice exam. So what I'm guaranteeing you is I'm not going to have this be option A and this be option J, and you're having to spend hours trying to figure out what I was trying to get you at. I would simply not have put that down. I might have put 3-hexanone, which would have been the absolutely wrong compound. I might have put 2-hexanal because I'm not sure you know the difference between an aldehyde and a ketone. And I might have tried a bunch of other stuff, like maybe I would have put 2-pentanone because I'm not sure you can count. I mean, that's not really a great answer. So anyway, understand that there is a right way to number things, but as long as your name unambiguously describes the structure, we're going to call it good. And so, yeah, hopefully that provides some reassurance. That being said, with this problem, we have to now decide what's the longest chain that contains the highest priority functional group. Go ahead. So format question on the exam, will there only be 4 options for problems? No, some problems will have more. I never made the promise that it would only be A through D. We'll have some more to say about the exam later. All of them won't have A through J. Yes?
So on the chart that has all like the suffixes, it says oil chloride for halide. Would that change like oil bromide?
Right, yeah, good question. If this were a bromide, if this were Br, we'd just say bromide. Yeah. It's the oil, whatever, however you want to say that, yes. And then the corresponding atom that's right there. Good. All right, so we got to try a few different ways of numbering. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. I got to choose the longest chain that contains the highest priority functional group. I know that some of you are saying, okay, well, what would we do if it was a tie? I'm not going to put you in that situation. Okay? Some of you are like, make it a little bit worse, let's do that. And I'm saying, no, I don't want to. What I'm trying to communicate is that there is a level at which it's no longer useful to be worrying about the nomenclature rules. And what I'm trying to demonstrate is the level at which I want you to understand them. So your root has 2 parts. You've got a number of carbons part. That's going to be hept. And then you have the second part of the root, which tells you number of double bonds or triple bonds and their locations. So we have double bonds. There are 2. So we're going to need to specify that there are 2 double bonds and their locations. Yes?
So, just like going over the study guide, there was like one question. So kind of like right here, I got it starting on the ketone, where it goes 1, 2, 3, starting on that first carbon. What situation do you like start on like whatever makes the longest chain? Like this molecule could be like deca if I started like at the end of the butane.
Right, so the reason I don't start here and number all the way there is because this chain doesn't contain the highest priority functional group.
Okay.
Yep,
Okay.
that's all there is to it. Yep.
So because that carbon that you labeled 1 isn't coming directly off of that chain.
Because it's not, we have to, let's identify this chain with highlighting. What I'm saying is the chain that gives you the root, the length of that chain has to contain the highest priority functional group. And no, it doesn't matter that this chain is longer.
Okay.
Yep. Okay, so we got to have specify 2 double bonds and their locations. The second part of the root for double bonds is -ene. Because there are 2, we will say diene, as in help, I am dying. That's an Ochem dad joke for you right there. It's a famous one. Diene, now we have to say what atoms the double bonds are on. By convention and arbitrary rule, we choose the first atoms, the lowest number atoms for each double bond. So 2 and then 4. So hept 2,4-diene oil chloride. There's technically a rule for tacking the suffix on the root if they're, but I don't care what it is. The dash and the suffix is just fine for me. You might see somebody drop the E and put the O right next to the end. That's fine, but it doesn't matter. So now we're to prefixes. We've got the appropriate suffix, the root with the name and the number of double bonds. Everything else, all the other things, are going to be substituents or appendages to the main chain, and we're going to name them as such. We need to know their identities and their locations. So the 1 carbon, a CH3 group, we're going to name according to the same pattern that we name main chains, only instead of calling this methane, we're going to call it methyl, as in a methyl group. The other chain is a 1, 2, 3, 4 carbon chain. We're going to name that according to the pattern in the study guide, but instead of butane, we're going to call it a butyl group. All right, and now we simply need to say their locations. This is a 2-butyl group because it's on carbon 2. And this is a 5-methyl group because it's on carbon 5. And now we tack the prefixes in front of the suffix. And there is a rule for the order that you put them in. I think the rule is alphabetical, but sometimes you might get tempted to put them in number order rule. I do not care. That doesn't matter to me. So don't worry about that. 2-butyl, struggling to write, 5-methyl, hept 2,4-diene oil chloride. All right, you with me so far? If you wrote 5-methyl 2-butyl, that would be fine. If you wrote 5-butyl 2-methyl, that would be wrong because the methyl and butyl groups would be on the wrong carbons. All right, we are not done yet because, I don't know, have you ever been on I-70 driving into Colorado and you're sort of getting around to Golden and you think you're almost to Denver and the sign on the road says, "Truckers, you are not down yet," because there's still a big grade to go down. We are not down yet. There's still some work to do. I don't recommend driving on I-70. It's a long and boring drive, so don't do it. But the reason we are not done yet is because this name does not unambiguously specify this molecule. We talked about this last time. You have to say what the E and Z configuration is. If you don't, the name that we just did, let's see, 1, 2, 3, 4, also works for this compound. And those are 2 different compounds. Remember how we talked about how you can't rotate around pi bonds, around double bonds, because that would break the pi bond. It would destroy the side-by-side overlap of p orbitals. You can't interchange these two compounds by simple rotation around this bond. The same is true for this one. So you have to say, so if we don't have any other word in the name here, we can't tell whether we meant this one or this one. These two compounds are actually a kind of isomer. They have the same molecular formula, same molecular weight, same connectivity, same things attached, but their shapes are different. They are called stereoisomers, stereo for 3D shape. You learned about that a little bit in general chemistry, though it might have been a little difficult. We talked about cis-trans last time, but we have to have a way of saying which stereoisomer do we mean, and that's where we go E and Z, right? So each double bond here needs an E or Z configuration. We went through how to do this last time. The bond between 2 and 3, we consider that by first conceptually dividing the bond in two, and we're going to focus on carbon 3 first, asking what is carbon 3 bonded to, and it's bonded to a hydrogen and a carbon. Carbon is heavier than hydrogen, carbon wins, and this becomes the group that I'm going to be comparing and talking about when I decide whether the molecule is E versus Z. Now if we go to carbon 2, the next two groups attached to carbon 2 are a carbon and a carbon. That is a tie. So before we can decide who's the highest priority group, we have to write down, the tiebreaker is all the things that are attached to that carbon. So blue carbon 1 is attached, and I'm going to write these in order of weight, once to chlorine, twice to oxygen, and once to carbon. The carbon below is bonded twice to carbon and twice to hydrogen. So now an atom by atom comparison, chlorine beats carbon, and we have a winner. Therefore, the two groups that we've identified on either side of the double bond are opposite each other, so that double bond is what configuration? Has to be E, okay? We're going to call it 2E because we know we have two double bonds from the name. If I just put E at the front of my molecule, I'm not going to know whether I'm referring to the first double bond or the second. So I need a 2E in parentheses at the front of my name. We can do this again with carbon 4. I guess I got to use a different color for carbon 4 and carbon 5. Carbon 4 is attached to a hydrogen. I'm going to erase sort of what I drew here. Carbon 4 is attached to a hydrogen and a carbon. Carbon is heavier than hydrogen, so that carbon wins. On the left-hand side, carbon 5 is attached to a methyl group and an ethyl group. They're both carbons, so we invoke the tie-breaking procedure. The carbon on top is bonded twice to a carbon and twice to a hydrogen. The carbon here in the methyl group is bonded once to carbon and 3 times to hydrogen. We go down the list. That's a tie. Oh, we have a winner. Carbon beats hydrogen. The two orange groups on either side of the double bond are the ones we are talking about, and therefore this double bond is Z. They are on the same side. Yeah, yuck, yuck, yuck. Love that every time. Never gets old. Okay, so that's the right name of our molecule. Okay, that took a while, but you got to approach it systematically, bit by bit, and you'll get there. All right. So we don't have a lot more time to focus on that, and frankly, worrying about it in any more depth than I have just shown you is not worth your time. I will say one more thing that I said in the announcements. If you look at your study guide, there are cases where in parentheses at the front of the name, you have other designations that you don't know about yet, R and S. It is okay that you don't know about those yet. I did not intend for you to know about those yet. I put them there so that the answers would be complete, so that at the end of the semester, if you want to go back and review and practice, you can have the full answers. We will learn about what R and S mean in chapter 5. Okay, so ignore the R and S portion of the name. We can explain more about that later. Okay, good. So now what we're going to do now and Monday is talk about how functional groups are related and also the interactions, intermolecular forces between molecules are related to a lot of the things that you have experience with. So later on in the class, we are going to learn some analytical chemistry techniques for detecting functional groups. For example, how do you know that a certain molecule is a carboxylic acid? How can you tell that? And there are very simple experiments you can do in our department and in any chemistry department to determine whether something's a carboxylic acid or not. But in reality, your nose and your taste buds are already tuned to a lot of this. And it's actually bad practice to go in the lab and say, I wonder what this is, and taste it. That's a terrible thing to do. Never do that. Nevertheless, you have experience with a lot of these functional groups in your day-to-day life with things that you can taste and smell. So, carboxylic acids, like acetic acid, which actually is vinegar. How do they taste? How does vinegar taste? It tastes like vinegar. Thank you. All right, what else? It tastes kind of tart, maybe sour. Tastes acidic. All right, that helps too. Right? It's like telling me that salt tastes salty, which is true, but okay. So carboxylic acids taste tart or sour. So why is lemon juice sour? Because it's got a lot of citric acid in it. Okay, or those Sour Patch Kids or lemon heads, again, citric acid. Acids taste sour. Depending on the length of the carbon chain, the carboxylic acids can smell kind of like vinegar, or they can start to smell stinky. So you put 4 carbons on, and you have something that's would be technically called butanoic acid, though most people use the non-standard name. This is the other reason why we don't worry too much about nomenclature, because as soon as you learn about it, you learn that people call things what they want to call them anyway, even though it's not the correct name. So butanoic acid is sometimes called butyric acid. This smells like vomit, and it also smells like, I would say, probably dirty socks. Though a certain mix of these carboxylic acids can sometimes smell okay. So if you like blue cheese or other kinds of smelly cheese, sometimes it has some of these carboxylic acids in them. Okay. Let's see. Esters are closely related to carboxylic acids. Only the oxygen of the acid isn't bonded to a hydrogen. It's instead bonded to another carbon. So here is an ester that's called, again, this is not a standard name, it's just what it's called, isoamyl acetate. You don't need to worry about that name. The acetate refers to this portion. This smells like banana. Some of you maybe, I don't know if they still do this in high school chemistry labs, but you can actually do this on the benchtop without a huge amount of equipment and create a lovely banana smell. So this is used as a, yeah, go ahead. Is it used for jelly beans? I don't actually know, but food science people. Right. It is used, the various esters are used for flavoring things, yeah.
I'm studying food science, so there's actually a lot of, there's flavor chemists.
Okay.
They literally do this. Like
Okay.
They know all of the chemical compounds, what they taste like, what they smell like.
Okay.
They combine them to give things flavor.
All right, so if you want a more complex bouquet of flavor and smell than just straight banana, you can mix some of these things and match it. Very good. Thank you. Thank you from our food scientist. There's this one's more complicated, but just to show you sort of the complexity of, and also how changing the structure of the molecule changes what it does to your taste buds and to your nose. Here's an interesting molecule. I don't know the name of it. I also don't really care what the name of it is, but this one smells like strawberry. Yes, memorize this. Which one of these smells like strawberry? No, don't do that. Okay. Let's see. Sugars taste sweet. Sugars are polyalcohols. So here is a sugar that is called dextrose or glucose. Same thing. It doesn't taste as sweet as sucrose. Could I draw you the structure of sucrose off the top of my head? Sort of, but I might get it wrong, so I'm afraid to. Anyway, various sugars differ in the placement of these OH groups. So in one of them that's called galactose, this OH group is actually up instead of down. By the way, I just drew this in a very strange way that you may not understand what the heck I just did. That's okay, you're going to learn about that in chapter 4. That's called a chair conformation of a six-membered ring. Let's see. Oh, another one that would be good to know in terms of your ability to smell is amines. So the simplest amine is ammonia. How does that smell? It's kind of, I don't know, I've heard it described as acrid. It sort of makes your nostrils flare, and if you have nose hairs, they tend to curl and get irritated. Amines generally don't smell very good. They smell sort of acrid and corrosive. If you get to longer and more complicated amines, which I'm not going to draw you any examples of this, they smell like rotting fish. Okay. Now, one of the things you know, if you can smell something, that means the molecule you're smelling is volatile enough to go from where it was to be in the air, right? How else does it get to your nose? So if you're smelling, say, rotting fish, that means there are smelly compounds that are evaporating from the fish or becoming volatile enough to get in the air and then travel to your nose. And smell travels pretty fast. It's I don't know what the rate is, but it's as fast as molecules sort of diffuse into each other. So this allows us now to talk about something you may have had experience with if you like seafood. So if you go to a seafood buffet, they have lots of lemons available for you. What the heck is going on with the lemons? Because it tastes good on fish? Is that what's going on? It might be. Lemon is a sour flavor. Maybe you like to mix flavor. There's another reason for that. Go ahead. Yeah, exactly. It's to neutralize the amines so they get less volatile. Amines are bases. And what did I just tell you about lemon juice? It's acidic. It's citric acid, right? So if you have lemon juice, which has citric acid, which we are going to abbreviate as HA, and then you have your stinky fish amine, and you squeeze your lemon all over your fish. Let's suppose your stinky fish amine looks like this. Here is your acid, here is your base. pKa of your acid, carboxylic acid pKa is generally around 4. Draw the conjugate acid and the base. So here is citrate. And here is the conjugate acid of your stinky fish amine, only now it's the ammonium. Okay. So it's acid-base chemistry. If you do that, you won't smell the fish stink as much. Why do you think that is? Okay, you think since it's charged, it's not going to leave the solution quite as much. Good, and that has to do with the intermolecular forces we're going to talk about. The neutral molecule is more volatile than the charged molecule. The charged molecule more readily gets attracted to water molecules in solution. So it's happy to stay dissolved and not go into the air. The amine is much more readily escapes water and gets to the air. So this one is volatile and you can smell it. This one is less volatile. So understand that when you go to the fish buffet, which I'm not a big seafood fan, so I'm sorry if I'm criticizing this, the lemons aren't there only for your taste enjoyment, but also to control the fish smell. Anyway, chemistry, right? So with that, just understand that you can sense the functional groups in your surrounding. Yeah?
Does that reaction like happen in the air, or is it just like directly in the street?
Could it happen in the air? It's likely happening on the fish itself as you put the lemon juice on it. Yeah, good. Okay, let's see. Yeah, over the break, we were down in St. George around New Year's with my in-laws and some of my wife's brothers, and they wanted to drive down to Mesquite to go to the prime rib and crab leg buffet at some casino there. And my boys were thinking that sounded great, so I decided to go. Amber, my wife, wasn't interested at all, so she didn't. I really shouldn't have. It was wasted on me because I don't really like crab or fish really of any kind. Anyway, it wasn't that great of an experience, but there was definitely a lot of lemon going on with the crab legs, and I just sort of sat there. And so anyway, I don't know what that has to do with chemistry. All right, next we want to talk about intermolecular forces. And I like to call these non-covalent interactions. That's actually maybe the term that's best used. Your text uses the concept of intermolecular forces to help you predict what the boiling point or melting point of some organic molecule would be, and also whether or not it might be soluble in organic solvent. We are going to address the solubility issue. We're not going to talk too much about boiling point or melting point. If you are preparing for a standardized exam like an MCAT or a DAT and you think they're going to ask you about boiling point or melting point, you need to come back to this chapter and read a little bit on it. It's not that hard, but it's also not really worth a lot of our time right now. Let's discuss these intermolecular forces or non-covalent interactions. Basically, we are talking about attraction between, or attraction or repulsion really, between either full charges or partial charges. Or another way of saying partial charges might be like a non-uniform distribution of charge in a molecule. And to some extent, you can mix and match these, all right? So let's first talk about the kinds of charges slash partial charges slash non-uniform distribution of charges that you can encounter in an organic molecule. And then we'll talk about mixing and matching these to form various intermolecular forces or non-covalent interactions. We'll talk about how these are related to things that you see in your day-to-day life. So one is full charges or ions, and these are generally thought of as point charges, and they're attracted to each other as follows Coulomb's law. So a sodium ion, or a chlorine ion, or a potassium ion, or a conjugate base of a carboxylic acid, that's an ion. Like charges attract. Whoa, anybody want to correct me? Waving hands saying, wait, I thought. Opposite charges attract, like charges repel. You've got Coulomb's law. I'm not going to write it down. We don't need to calculate anything. Okay, so that's one example of charge. Then you've got dipoles. Dipoles and they're related to bonds where the two things in the bond do not have the same electronegativity. So an example of a dipole might be HF. in the molecule HF, where you know fluorine's more electronegative than hydrogen. So the hydrogen should have Greek letter delta, positive charge on it. The fluorine should have negative charge on it. The Greek letter delta indicates it's not a full positive or negative charge, it's a partial positive and negative charge, as if the electrons in this bond were leaning towards the fluorine. And you've probably seen this symbol before for a dipole, where we've used an arrow with a plus at the end of it to indicate that this is a plus. This is the electron poor end of the dipole, and this is the electron rich end of the dipole, right? Yes?
Is the dipole very similar to like the partial charges we see in resonance?
Is the dipole related to partial charges we see in resonance? I mean, same idea, not full charges. Yeah. Okay. Dipoles are vectors, so and they basically represent a line. So if your molecule isn't linear, you add together the dipoles to get the overall dipole of the molecule. Classic example of this is water. We have individual bond dipoles that are here and here because oxygen's more electronegative than carbon. The overall dipole of the molecule adds together to look like that. Okay, you can add them together like vectors. But you can see how in the same way that a positive charge might be attracted to a negative charge, you could have the negative end of a dipole attracted to a positively charged ion, right? Or you could have the negative end of a dipole attracted to the positive end of another dipole. This is what I mean mix and match. You maybe were taught there's ion-ion interactions, there's dipole-dipole interactions. I'm telling you mix and match. There's also ion-dipole interactions. And you don't need to memorize them because they're all based on the same thing, which is attraction of opposite charges, either full or partial. There's another one that you probably don't know about, but we are going to talk about because it has to do with organic molecules, quadrupoles. A quadrupole is a molecule that doesn't have a dipole, but nevertheless, there's not a uniform distribution of charge in the molecule. This tends to happen when dipoles cancel out, and yet everything isn't the same. So let's look at a classic example of this in organic chemistry. I am drawing for you the molecule benzene. Each carbon in benzene is sp2 hybridized, and each of those sp2 hybridized carbons is bonded to a hydrogen. I will tell you as a matter of fact that an sp2 hybridized carbon is more electronegative than a hydrogen. So you have a lot of individual bond dipoles where the carbons are electron rich or partial negatively charged, and the hydrogens are electron poor. Now, benzene is nonpolar. The reason it's nonpolar is because all of its individual bond dipoles cancel. It's symmetric, right? So do you see how this dipole is vector canceled by that dipole? Yeah? And we can do this for all of the bonds in benzene. All of those individual dipoles cancel each other out. Nevertheless, all of the hydrogens are electron poor, and all of the carbons are electron rich. What this means is the hydrogens, if we want to use the color red here to be, or blue to be electron poor, you've got the edge of the benzene ring that is electron poor with a partial positive charge on it. And then we'll use the color red for, which we don't have, all right, fine, to be all of the carbons of the benzene ring are electron rich. Yeah?
So basically quadruples will not have an overall vector.
Right. Yeah, quadrupoles have no overall dipole vector. It's totally fine to call them nonpolar, but if you forget the quadrupole, you've missed something important. And you can have as before, you could have quadrupoles interact with other quadrupoles, you can have quadrupoles interact with dipoles, and you can have quadrupoles interact with ions. In fact, one of the most interesting things that people learned about chemistry in the past couple decades of the that sounds so long ago, the past couple decades of the 1900s. In the mid to late 90s, people began to appreciate that actually ions can bind to benzene. Remember, the face of benzene is electron rich. So I'm going to attempt to draw benzene sort of sitting on its side. These bonds in the front are jutting out towards you, whereas the hydrogens in the back are sort of oriented away from you. And people discovered, and again I'll use highlighting to illustrate, the face is electron rich, the edge is electron poor, that you could have a positively charged ion, for example potassium, and potassium is actually is a decently large ion, so we'll color that in. In the gas phase, in a vacuum, it's actually pretty common to see the ion of potassium sitting down on top of that negatively charged portion of the benzene ring. We call that an ion quadrupole interaction, although sometimes a cation quadrupole interaction, though sometimes people call this a cation pi interaction because there are double bonds in the benzene ring where the extra electron density is. In any case, you can also mix and match. You will see often that benzene molecules associate with each other. Let's see if I can, there we go. Oops, lost the red. So I have one benzene ring, and it turns out that I can have a second benzene ring where the electron poor edge of the second ring sits down and contacts the electron-rich face of the other ring to form this sort of T-shaped dimer, right? You can also have situations where one benzene ring stacks on top of another, though you wouldn't predict that they would stack directly face to face. Why not? Like charges repel, right? See how much you can predict. But if you did calculations or did observations, it's actually what you get is this offset stacked dimer where the electron poor edge of one benzene stacks on the electron rich face of the other benzene. So yeah.
So if all like the dipole interactions cancel each other out, why is it more electron rich inside?
All of the dipoles are still there, but the overall molecule doesn't have a net dipole. So yeah, it's weird that it can be that way, but that's the definition of a quadrupole. There is no overall dipole, and yet the edge of the benzene ring is electron rich and the face is electron poor. You can see this in an electrostatic potential map, which we could draw here in the program Spartan. I think it should have it. Yeah, let's download and go. You can see on the color here towards your left, blue is more electron poor, red is more electron rich. And you can see that the edges of the benzene ring are sort of blue, whereas the face is yellow. You can see that there's a difference in the electron density in this ring. Yeah.
Does this come into play also for tetrahedral molecules or carbon tetrahedral?
Can this be true for tetrahedral molecules? I think you just mentioned carbon tetrachloride, which you learned is nonpolar, but has the same sort of issue. All the dipoles cancel each other out. Nevertheless, you'd predict the carbon would be electron poor. Sure, though that's small enough that the carbon really isn't exposed, and so it doesn't really have any consequences. Yeah. All right. The last sort of intermolecular force situation we need to talk about is something you learned about called dispersion forces. These are called induced dipoles. This is a situation where a molecule has no permanent dipole, no real quadrupole, and yet, if you let the molecule get close enough to another molecule, things start to happen. So I'm going to draw just a hydrocarbon chain with all of the hydrogen shown, so you can have an idea of the space that's taken up by the atoms and electrons in this molecule. And I'm going to use gray to highlight in gray to represent maybe no, fine. At some point I can say how big I want the gray to be. No, that's fine. I'm going to use gray to highlight the electron density that would be around each of the atoms in this molecule. And gray is just going to indicate that there's not a huge amount of polarization in this molecule, that it's basically somewhat uniform. Oh, no, there we go. Now, if I have two of these molecules, depending on how close they can get together and approach each other and how complementary their shapes are, as they approach each other at an instant snapshot in time, it's not permanent, the electron clouds on the electron cloud on one molecule will adjust itself so as to be instantaneously complementary to the electron cloud on the other molecule. So in one instant, this face of the molecule on top is electron rich, and at that same instant, the face on of the other molecule, the corresponding face that's close, becomes electron poor. And that leads to an instantaneous attractive force. Now that's not permanent, and of course in the next instant, after a certain amount of time, this face might end up being electron poor, and this face might be electron rich. That's what we mean by an induced dipole. It's sort of like instantaneous charge complementarity that happens if molecules get close to each other and if their shapes are similar enough that there's a lot of contact between them. Yes?
Can we just like choose to be positive or negative?
There's no choice. It just is related to the fact, I mean, of course there's choice. I didn't mean that. Agency is a very important gospel principle. I don't know, it's a philosophical question as to whether electrons have agency. I'm not prepared to debate that. What I'm saying is that because electrons repel each other, as two molecules get close together, their electron motion will correlate with each other so as to be as mutually out of the way of each other as they can possibly be.
Is that van der Waals?
And that is the induced dipole van der Waals interaction. Okay. With that in mind, I want to just take a minute and start talking about questions that you have some experience with. We've talked about ions, and that ions are attracted to each other. And at some point in your past, you learned that ionic bonds were strong. Nevertheless, if you take a cube of sodium chloride or a grain of sodium chloride and you put it in water, it dissolves. And once it's dissolved, the sodium ions are no longer close to the chlorine ions. So how are ionic bonds strong, and how does sodium chloride dissolve in water? Go ahead.
The attraction between the water and the ions overall are more favorable than just one bond.
So what you're saying is that the individual water molecules can interact with each ion, and those ion dipole interactions totally replace and pay for the ion-ion interactions that we lost. Yeah. Strength is a relative thing. You always want to talk about strong relative to what? The ionic bond is strong relative to those ions being infinitely separated in a vacuum. Sure, you got to put in a lot of energy to make that happen. But as long as you can pay for the interaction you're using by replacing it with interactions with water molecules, you're good to go. That kind of thing is behind every biological process. So we'll talk more about that on Monday. Have a good weekend.